Hello group, welcome to chapter 2.1 lesson on area applications. We're going to be looking at composite figures. Here's a simple definition for a composite figure. It's anything composed of or made up of simple shapes. It has to be two-dimensional. We'll be looking at composite solids later on when we examine volume. So here's a couple of little graphics to show you, you can make some pictures with composite shapes, and it's nice to put them together. Quite often when we're doing these types of problems, we were trying to actually take them apart. So for example, a house may be made up of rectangles, a square, maybe a trapezoid or a parallelogram. We can look at the individual shapes, and if we can find their areas, we can do problems on in the two-dimensional. So quite often we're painting a surface or maybe laying some exterior board or covering over something, and we just need to know what square footage we're dealing with so that we can purchase the material and then look at a cost for the job. So that's some good type of applications. Here's a formula sheet which you'll receive in class. This was given in the EQAO year in grade 9, and these are all the base shapes and their formulas for both perimeter and area. Rectangle, parallelogram, triangle, trapezoid, circle. Try to memorize these formulas, but you'll have this reference sheet to use in your classwork and also on the unit test. So I'll just also point you to the textbook. In the back cover of the textbook, you'll find diagrams and formulas there as well. So if you're without your formula sheet in class, you can use your textbook. Let's dig in right here. There's two examples which are shown in the textbook. The first one is found on page 68, and it just asks you to determine the area of a composite figure and to describe the types of shapes that are present. So you'll see this solution explained in the text on page 68. And I've got a convenient little drag over here which I can apply to my diagram, and that helps to give you a little bit of perspective. So we have some parallel sides, we have a nice arch which reveals a semicircle, and we have a trapezoid. So we could break that up into probably a rectangle, 16 by 24 and 3/4 inches. These dimensions are given in the textbook. We could think of that rectangle as actually having half of a circle removed from it. So in this example, we would just be looking at identifying the parts. We have a rectangle with width 16 inches and height 24 and 3/4 inches. We have a parallelogram with height 9 inches and base length 16 inches. And then we, of course, as mentioned, we have the rectangle with a semicircle cut out of it, which has a diameter of 16 inches. Because we have the formulas for all these shapes, so this is a simple matter of going to our formula sheet, applying the areas for the figures that are part of our overall shape, and then either adding them up or in some cases removing them. Give you an overview sort of how to determine the area of any composite figure. It's pretty common sense. We want to first identify the main shapes in the figure. Just need to know what they are. Need to be able to find the area formulas for them. If necessary, sometimes it's helpful to break the figure into smaller shapes. So a trapezoid, although it has an area for it, which can be found as half of the top length plus the bottom multiplied by the height. Another way of looking at a trapezoid is possibly a rectangle and two triangles. Depending on the shape of the trapezoid, it could be converted into just simply one triangle and a rectangle. So that's a good strategy, is to break up something into really basic shapes with simple areas, and if possible or if necessary, determine any missing dimensions from these shapes. That may require reading into the dimensions a little bit and adding parts, or it could be that the hypotenuse of a triangle is not given but the base and the height are. We could use Pythagorean theorem. Step 4 in the process would have us calculating the area of each shape and adding these up typically to give the overall area for the figure. Or in some cases we have to take away from the figure for any shapes that are actually not part of it. The final step in the process is really to state that final area with the correct precision and units. So precision referring to how many decimal places of information, and the units would just be making sure that all of our values are in a common imperial or metric unit. Okay, I'm going to just move on to example 2, which is found in your textbook on page 69. This one again is asking for the area of a composite shape, and actually rather this is example 3 on page 70. The introduction is that a carpenter has constructed the frame for a house and will nail pressboard over the frame to determine the area of the pressboard that is needed for the back wall of the house. We're just looking at the back wall here. I think we're going to assume that that rectangle in the middle there, 33.5 inches by 81.5, is a doorway. So we're not going to be nailing pressboard over that, I don't think. It's not stated in the question, but we can assume that that would have to be removed from the overall shape. So we notice we're given an angle here. We're given some equal side lengths at the peak of the house, and we're given the height of the wall and the base length along the bottom at 8.53 meters. So the first thing here to recognize is we have different units to work with. So if you follow through this solution, it's fairly involved, but a little description of the strategy I can include, and you can sort of follow through the steps and see if they agree with what your approach would be. First thing I would recognize with this problem is that the overall area to be covered is a large rectangle with a smaller rectangle removed, plus a large triangle on top. Step 2 would be to recognize that that large triangle is probably best separated into two isosceles triangles, because we need to find the height of that large triangle. So we will have to divide the full width by 2, and so the 8.53 is going to be cut in half to give the base length of the smaller isosceles triangles. Third thing is that we're starting to find the areas. So the large rectangle has a simple area of 5.75 meters by 8.53 meters. Since we're being asked to find the total area, and we're going to eventually relate that to the area of one sheet of pressboard, square meters, we would need to determine our area in meters. So I will have to convert the dimensions of the door frame into meters as well. In step 3, going back to our flowchart here, determine any missing dimensions from any shape. So we need to find the height of the smaller triangles, and we also need to find dimensions in meters for the door frame. So the height of those triangles can be found using the tangent ratio. Tan of 22 would be height divided by adjacent side, which would be 4.265 meters, which we've determined by just taking half of that floor length, 8.53. The dimensions of the door frame are, and we're using the equivalence, which is that 1 meter is 39.37 inches. So we can take our 33.5 and 81.5 inch dimensions and multiply those by that ratio, which in this case would convert each of the dimensions into meters. So we'll be taking 33.5 and dividing it by 39.37, or multiplying by its reciprocal, and likewise with 81.5, multiply that by 1 over 39.37. So that would convert our units, and we could move on to step 4. So continuing on with step 4, we can start to find out individual areas. The large rectangle would have an area of 5.75 by 8.53. That would be in meters squared. The area of the door frame can be found using length times width as well, and we'll call that A sub SR. So we'll use a label for the area. You can break it up into area 1, area 2, area 3, but I like to use a subscript which kind of matches the type of shape it is. So small rectangle SR and large rectangle LR, we can find the area of the large triangle. Since we were able to find the height using the small triangles, we can really still just use base times height divided by 2. Rather than using two small triangles, we'll just use the total base and the height and the base would be 8.53. The height would have been found in step 3. Moving on, in step 5 and 6, where we're really adding the areas and possibly subtracting any areas from removed shapes, we can return here and see that we'll have to add up large rectangle and large triangle and subtract off small rectangle. This area will be in meters squared because we have converted inches to meters in step 3. We'll use 2 decimal places of precision to match the precision in the height and the base of the wall. And finally, to conclude this problem, we need to convert the number of square meters of area to the number of sheets. So we'll just simply divide our total area by 8.9. This needs to be rounded up to the nearest sheet to ensure that enough is purchased. And I would just mention one more thing, that this calculation here of dividing by 8.9, I'll just copy it down here and show that this could also be thought of as area total, and then multiply by 1 sheet per 8.9 meters squared. And that's consistent with the rate conversion method that I introduced at the start of the course, because that way we're always multiplying by a rate, and the equivalence there is that 1 sheet of flake board or press board is 8.9 square meters. So that would give us an answer in sheets, where we would be dividing out our unit of area in meters squared. So that would conclude that problem. Okay, I'll do one more together here. Number 13, which is found in your textbook in this section. This is not one of the assigned problems, but it's going to help you with number 14 on page 74. So number 13 is determine really the area of a regular octagon. Here it has side lengths of 20 centimeters each, and so all the side lengths are the equivalent. And you can sort of look at this really as just a big square, actually, because it's going to be equal on the height and the base length, with some triangles removed. Let's see what that might look like. So it sort of recognized that in this case it would be easier to find the area of this octagon by considering a simple shape, which is a cube, or rather a square with some pieces cut off. And so in this case we would be able to determine the area of the square and subtract off the area of 4 triangles. Okay, so I'm going to go to the smartboard now. I'm going to do some writing here, because I'm realizing here that in order to find the overall area, we're going to have to determine some missing dimensions. So step 3, we recognize that what's missing in this is that we don't know the length of the height and the base of those triangles. Now, are those equivalent lengths? Well, if we look at the hypotenuse of all the triangles are equal, and because this is a regular octagon, all of these angles here are equal. That's one of the properties of a regular polygon, is that interior angle values are all equivalent. So that means that the supplementary angles on the other side of the line will be equal. And as soon as we know that, we can conclude that because it's an isosceles triangle, the sides are equivalent. So we have maybe use of a different indicator here to indicate double slash for equivalent side lengths for these triangles. Okay. Now from there, what I would do is I would call that dimension by a letter. So I might give it L for the side length, which is 20, and I might call this other value, we'll just call it X. Okay, so we have a lot of X's and a lot of L's. Now, by the Pythagorean theorem, we know that because the edges of the octagon are going to be perpendicular. At least the top and the side will be. Okay, and so we know we have a right angle in the corners, And that allows us to use the Pythagorean theorem. So using the Pythagorean theorem, we can find missing dimensions, and the relationship is that the square of the base plus the square of the height is equal to the square of the hypotenuse, which would be L squared. Well, we know that L is 20, so we have 20 squared on the right side, and we have x squared plus x squared, which is 2x squared on the left side. 20 squared is 400, which leaves us with twice the square of the triangle dimension is 400, which means that the square of the triangle dimension is 400 divided by 2, which is 200. So using our inverse operations, x would be the root of 200. Okay, that is approximately equal to 14.1, and that would be in centimeters. Okay, so we need to know that value because the area of the square is now, we'll use capital L and capital W for its length and width, and I'll indicate those as here and here. Okay, well, they're equal, so it's really, we can just call it by a common value, but L is equal to W. And in that case, L and W would be equal to little l, the length of the edge of the octagon, plus 2 x's. Alright, so that would be the length and the width of this square would be 20 plus twice this value, which we've just found out to be about 14.1. So that gives us 28.2 plus 20 is 48.2 centimeters. So the area of the square is going to be really, we could call it L squared or W squared. And we're going to put that value in at 48.2 centimeters all squared. So when we square this, we get area units, which are squared centimeters, and 48.2 squared gives us 2,323.24. Alright, so that's the area of the square. I'm just going to indicate that as area A subscript S. Now, the area of a triangle is base times height divided by 2 by a formula which would be base of x and a height of x, and we know that because the base and the height are perpendicular in this case. So it would be x times x divided by 2, which would be the square of 14.1 divided by 2. So 14.1 squared is 198.81, divide that by 2, and we get 99.405. Okay, now we're carrying a couple of extra decimal places here, so in the end result we could probably round this back to the nearest square centimeter, just to match the precision which was given at 20 centimeters for the initial length. So here we've completed probably steps 3, 4, and we're about to add areas, and in this case there's really no areas to add except, in a sense, add those that are to be subtracted. So the final calculation would be the total area of, we could call it the octagon, would be the area of the square, and I'm going to call the area of the triangle A subscript T, subtract, and keep in mind we have 4 triangles, so it'd be 4 area times the triangle, and that would be 2,323.24, subtract 4 times 99.405, and if we work that out, we get 1,926 as an approximate for square centimeters. So that would be the area of the octagon. Okay, so next time we meet in class, we'll be looking at some assigned work. There's a short little investigate on page 67, which you're going to be doing to start out. It's a simple composite figure made up of a semicircle, rectangle, and two trapezoids. You're going to be computing the area of this independently, then you're going to be trading solutions with a classmate to see how their approach compared to yours. With a partner, you can be looking at discussing a couple questions just to see if you understand this idea of composite figures. And you can work on completion of 9, 10, 14, and I'll be collecting number 12, page 74, which is a good problem where you're trying to find the area of an outdoor garage. It'd be very similar to the question I looked at, which was example 3 from your textbook. And there's lots of different shapes involved in that one as well. See you in class.